So if you see, this is a floating point unit implemented in IBM 360, and it consists of a floating point adder and a multiply unit, and it takes two operands. And once the instruction is decoded, it will be sent to this floating point operand stack floss. And every cycle it is going to take an instruction from this, and depending on whether it is an adder, add instruction, or a multiplier div instruction, and it will be sent to appropriate function unit. And these function units are not pipeline. And it can read the operands either from a floating point register file, FLR, or it can read the data from the memory, the storage. So actually from the storage, you will be put the data into FLB, floating point buffer, and from there it will be reading the data. And once the operands are available, then the instruction is sent to the appropriate function unit. And because the function unit is not pipelined, so it occupies that X number of cycles to execute that instruction. And once the result is available, then it will be sent on the result bus, and that will be sent to this FLR, floating point registers. And from there, if the actual destination is to the storage, then it will be sent to store data buffer SDB, and from there it will be sent to finally the storage. This is what the actual design they've considered. But if you see here, the overall performance is not improved because obviously the function units are not pipelined. And also another thing is, at any point of time, function units is holding only one instruction. That means the buffer associated with the function unit, you have only one entry. So unless and until the function unit is free, that buffer cannot accommodate any more new instructions into it. And that puts a back pressure on floss, and then you cannot read any new instructions from the floss. And over a period of time, floss is also going to be full, and then there will be a throttling from the front end side. So now this task of optimizing this floating point unit design is given to a scientist, Tomasello, and he came up with some modifications to this entire floating point unit design such that the overall throughput improved. And what modifications he proposed? If you see that, this is what he has done. If you just go back, so you can see here each floating point unit, you have one entry buffer, and also the result will be written to the floating point register file FLR, not anywhere. But what Tomasello made the modifications are, instead of single entry buffer for each of the floating point units, he actually considered multiple entry buffers, and he called those things as reservation stations. And also when the function unit finishes its execution, the result will be not just forwarded only to FLR, it is also forwarded to the entries which are sitting in the reservation station. If you see here, the result bus is replaced with common data bus CDB, and the data will be forwarded to the entries in the reservation station, also to the entries in the SDBs, store data buffers, also to the entries which are there in the FLR. So this way, what is going to happen is, basically, when an instruction is about to schedule onto the function unit, and if the operands are not available, in the previous case, we were not scheduling that, we were just keeping that in the floss itself. But whereas here, we can just forward, we can schedule that onto the function unit or send it to the reservation station associated with the function unit with a tag. If the data is available, well and good, we can just supply the data. If the data is not available, we will be sending with the tag. And the instruction is just sitting in the reservation station with the tag. And when the producer produces the value, because that value will be forwarded with the tag, now the tags are compared. And if any instruction waiting for this particular value whose tag matches, then automatically it takes the data into it. So this way, now we don't have to actually wait for a previous instruction writing the value into floating point register file. As and when it finishes its execution, the data can be forwarded. Operand forwarding is implemented here. And also another thing is, because we provided the tags, so based on the tags, we can actually, so when we forward, we'll be writing to a proper location by using these tags and so on. So as a result, we don't have to wait for the functional unit to finish its produce a value into a register file, and also we don't have to wait for operands to be taken from the floating point floss into the reservation station. We can just forward with the tag, and then anyway operand forwarding is there, and that is going to take care of the overall execution. So that with these small modifications, he actually achieved a good throughput for the floating point units. And the floating point operations typically take good amount of time, and with these modifications he achieved better performance compared to the old design, and they named this as IBM 36091, which released in 1966 or time frame. But if you see here, in 1966 he came up with this idea, and this actually is the heart of our current superscalar processors, where we have the reservation stations, will be forwarding the data, and the instructions are stored in the reservation station with the tag, and it takes care of the structural hazard, it takes care of true dependencies and everything. And that is the basic idea for the superscalar processors. I think it maybe after 20 years or so, the actual superscalar process people proposed and so on. But well before the actual superscalar process, this idea of reservation stations and so on conceived in 60s itself. Now I'll just explain this entire thing with an example to see how it actually achieves better performance and so on. Of course, this example may not give you too many cycle savings and so on, but at least we'll get an idea of how the number of cycles for executing some floating point operations can be achieved. Let us consider this example consisting of 4 floating point operations, and add, multiply, add, and multiply. And here you can see first multiply operation is dependent on the previous add operation, because F4 true dependency is there. Once F4 is produced by add, that can be taken by subsequent multiply operation. And similarly, second mul also depends on the immediate the add instruction, because there is an F4, right? And also, of course, you can see here there is an anti-dependency between second add and second mul and so on, right? And also another thing is the second mul is actually waiting for the value of F2 produced by first mul. So there are dependencies and so on. Now we'll see how this is computed using IBM 36091 model of floating point unit. And we made some assumptions here, and our floss is going to dispatch up to two instructions in every cycle, because we have 2 floating point units, one adder and one multiplier. If we have 2 operations, one add, one multiply, we can just schedule. But if you have 2 add operations, then we can schedule only one onto it. And instructions can begin execution in the same cycle in which they are dispatched to the reservation station. And similar to the original design, the functional units are not pipeline. And add takes 2 cycle latency, whereas a multiply takes 3 cycle latency. That means once we give an instruction to an adder, the result will be produced after 2 cycles. And if we give the instruction to multiply, the result will be produced after 3 cycles. And here we have a 3-entry reservation station for adder and 2-entry reservation station for multiplier. And we have 4 floating point registers in the floating point register file. And so there these values are F0 contains 6, F2 contains 3.5, and so on. And each entry in the reservation station has 4 fields. One is a tag 1 and source operand 1, and tag 2 source operand 2. And we also name each of these entries in the reservation station with some numbers, right? So here 1, 2, 3. Actually, there is a typo. It's in the multiplier. It's a 4 and 5. It's not 1 and 2. So in the first cycle, we are going to dispatch 2 instructions. We dispatch W and X in the program order. First W will be issued, and then the next is X is issued. So now if you see here, W is add F4, F0, F8. So we'll be issuing that to the reservation station associated with the adder. And it has two source operands, F0 and F8. Because the values are already available in the FLR, so we'll be reading the value. F0 is 6 and F8 is 7.8. And we send the data, we read the data from FLR and send it to the reservation station. When we dispatch an instruction to the reservation station, we'll see if the operand is available. If so, we'll read the operand directly. If not, we'll send the tag. But here in this case, the operands are available. We'll be sending the data directly. And the tags indicate 0. That means that whatever the value that is there in the source operand field is the actual value. And we make that entry corresponding to W, saying that right now adder is performing or executing W instruction, and that is located in the entry 1 of reservation station adder. And add is going to produce the value into F4, right? So that means we have to come to FLR, floating point register file, and corresponding to F4 entry, we have to make this entry busy, indicating that whatever the value that is there in F4, the data field, is actually stale copy, and the new value is going to be ready. That is what is indicated with the busy bit. And who is producing the value? It is going to be produced by an instruction which is sitting in reservation station entry 1. That is what we have given here, tag field 1. When the busy is S, and tag is going to specify from which location we are going to get the data for the data field. And the tag field is 1, indicating that we just go to reservation station entry 1, which is pointed to W instruction, right? That is what we have given. The next second instruction in the same cycle, because 2 instructions can be issued per cycle. Now, if you see here, a multiply F2, F0, F4. It reads 2 operands F0 and F4. When I just go to FLR with F0, the value is available because busy is not S. So as a result, data is actually, the data field contains the actual value. So we just take the value 6 into it. And F4 is, when I go to FLR, F4 says this is currently busy, and reservation station entry 1 is going to produce a value. So we are going to take that 1 and put it into the tag field in the multiplier reservation station entry for the second operand. And that's the reason why, if you see the 4th entry in the reservation station, which is associated with the multiplier reservation station, so the tag 1 is 0 because your F0 is already having the value. So the 6 is stored in the data field, and the tag 2, which is going to be produced by previous add instruction. So we just put in the tag 2 field, we just put the value 1. And this multiply operation is going to write the result to F2. So we'll just again go back to FLR and update the entry corresponding to F2 by making busy S and the tag field to 4, because this entry is corresponding to 4th entry in the reservation station, which is producing the value for F2, and that is what we mentioned here. So basically now 3.5 and 10 in 2 and 4 in the FLR are actually stale copies, and they will be updated with the new values produced by instructions sitting in reservation station 4 and reservation station 1 respectively. Now in the next cycle, cycle 2, again 2 instructions can be issued. So the Y and Z we are going to issue in the in order, and Y is corresponding to add F4, F4, F8. Right? Now this is an add instruction. So basically we are going to make an entry, we are going to use an entry in the adder reservation station, and the next free entry we are going to take it. So let us consider 2 is the next free entry, and we just take that entry for storing this instruction, add instruction. But now the first operand is F4. But when I go to FLR, it says that the value is not the correct up-to-date copy, and it's going to be produced by an instruction sitting in reservation station 4, right? So that is what we are going to do. So the F4 value, right? F4 is, sorry, F4 is basically 1 is going to produce, right? Yeah, you can see here. So F4, the tag value is 1. So we take that value 1 and put it into the tag field of this entry. So that means if you see the second entry in the reservation station, tag 1 is actually pointed to 1, indicating that the value, the instruction which is sitting in the reservation station entry 1 is going to produce the value. And that is what we mentioned here. And the second field, second operand is F8, which is there directly in the FLR. We take that 7.8. And then this value is now going to be updating the F4 register. So again, we just go back to FLR and change the tag field to 2. Previously, the tag field here is associated with the 1. Now it is going to be 2. Why are we doing this? Because if any other instructions, subsequent instructions coming, and if they are trying to use F4, and they have to get the value from the latest add instruction rather than the previous add instruction. And that is what is indicated here. And multiply operation, we have not done anything right now. But the next instruction Z, which is a multiply operation, and which is going to update the value of F8 and try to read the values of F4 and F2. For F4, you can clearly see now the tag field is 2. So I'm going to put in the tag 1, we are going to put the value 2. And the data field is empty because it is now going to be produced by instruction sitting in reservation station number 2. And F2, if I just go to FLR, it says that entry in 4, which is going to actually produce the value for this F2 register. So we just put that 4. So now after end of cycle 2, this is what is the status. Reservation station adder contains 2 add instructions. The reservation station for multiplier has 2 instructions, and the floating point register file FLR, 3 registers are going to be updated, and F0 is as it is because we are not changing the F0 value from any of these 4 instructions. Now cycle 3. Okay, so in the cycle 3, because first add instruction issued in the cycle 1. So after 2 cycles, that means the cycle 3, we are now going to get the value for the first instruction, first add instruction. And what is the value it produces? It's a 13.8. And where are we supplying that value? So for that, we have to see wherever the tag 1 is there, we will be forwarding the data to that. So if you see in the adder, the second entry is actually waiting for the data from tag 1. Similarly, multiplier entry 4 is actually waiting for tag 2. The tag 1, the value 1 is there in tag 2 of entry 4. That is also waiting for that value. And previously it used to be there 1 in the tag field of FLR, but now that is updated with F2. So as a result, we don't have to entry 2. So as a result, we don't have to write anything in the FLR, but we have to forward the data to 2 entries in the reservation stations. So we'll be updating that, and that is what is seen here. So now the second entry in the adder reservation station, you can see the tag 1 now is becoming 0, and the source field is now 13.8, which is the added value of the previous add instruction. And similarly, in the fourth entry of reservation station, that is a multiplier reservation station entry, the second tag is now 0 and the data field is 13.8. And then we'll continue further in cycle 4, the next cycle. Now again, because the next cycle still, because add instruction now got the second add instruction now got the data. So now from now onwards, it is going to take 2 cycles. And similarly, multiply operation also got the data now. So it is going to take 3 cycles from now on. So in the next cycle, there is no change in the status of reservation stations and the floating point register file. So nothing is changed. But in the cycle 5, now the add instruction, second add instruction is done. And that value 21.6 is forwarded to all the places wherever the tag 2 is there. So one of the entry is reservation station entry 5 in the multiplier, and that is where we just forwarded. And also we forwarded the data to one of the floating point registers. And similarly, in the next cycle, cycle 6, because in cycle 3, multiply operation got 2 operands. Now cycle 6, it completed. Now that value is also written to appropriate things and so on. And similarly, now after this, so now you are going to get the values and for the second operand of the multiply operation, and that will be again, it takes another 3 cycles and so on. Basically, after 9 cycles, all these 4 operations are going to be done. But if you are just considering the normal way, then it is going to take 10 cycles. Suppose this is a simple example, but if you consider a floating point operation based application with a large number of floating point operations and so on, then you can definitely see the improvement because of this pipelining and the reservation stations associated with this. Though the functionality is not pipeline, but because we are sending the data and the data is sitting in the reservation station, and we'll be forwarding operands directly from the functional unit to the reservation stations and so on, which reduces the overall execution time. And this is basically the main idea behind any of these current superscalar processors implemented. So in summary, the Thomas-Solow algorithm consisting of 3 things. One is an issue. So next instruction will be taken from the instruction queue in the FIFO order. And if there is an entry available in the reservation station, then we'll issue this instruction to the reservation station. And when we are issuing the instruction to the reservation station, we'll also check whether operands are available or not. If operands are available, we'll be forwarding data as it is. If not, then we'll be forwarding the corresponding the tag from where the data is going to be available, whether it is the tag of the register or the entry of reservation station or whatever. And if there is no entry available in the reservation station, then this instruction is going to be just waiting in the queue itself. So the program order issue, and then it will be issued to the reservation station depending on the availability of the entries. And once we issue the instruction into a reservation station, now we try to execute the instruction if the operands are available. If both operands are available, then only we are going to execute. So that takes care of your read after write hazards. So only if the operands are available, we are issuing this instruction to the function unit. And if the function unit is also should be available, right? If the function unit is not available, then we'll just keep the instruction in the reservation station. That also takes care of structural hazards. And here we just, in this Thomas-Solow algorithm, we just consider only floating point operations and so on. And memory operation load and stores, they are going to be executed in the program order. And also for control instructions, they have not considered any branch prediction mechanisms and so on. And the write back, once the function unit finishes its execution, data is going to be placed on the common data bus, and that will be sent or forwarded to the registers, also to the reservation station entries and so on. So as a result, any instruction which is looking for the value, it need not read from the register file. It can directly get it as soon as function unit finishes its execution. So because of these optimizations, he was able to extract better performance for processing the floating point operations and so on. Of course, later designs, they actually even consider floating point function unit itself is pipelined and so on. But yeah, so this is basically the summary of this is, so the superscalar processor, the idea actually came from this Thomas-Solow implementation of floating point operations. Right. So if you have any questions, you can ask me. Otherwise, I'll just continue with the rest of the topics. Okay. So if you see in the superscalar processor implementation, because we said like execution unit where instructions are going to be executed in an out of order fashion and so on, and how that is actually happening, dynamic execution core, if you see. So there is a dispatch buffer. From there, we'll be dispatching the instructions. And while we are dispatching, we'll be actually performing this register renaming. That is what is given here, ARF and RRF. And we'll also make an entry in the reservation stations for each of these dispatch instructions. And from there, instructions are going to be scheduled onto different various functional units, depending on the availability of the functional unit as well as availability of the operands. And whenever any functional unit finishes the execution, the data will be forwarded, placed on the bus, and that will be connected to RRF, connected to the reservation stations, and so on. And we'll have, after that, there is a completion buffer or a reorder buffer. And from there, the instructions are going to be committed in the program order. That is what is given here, maintains a sequential order of all the instructions in flight. That is done by the reorder buffer. So instruction dispatch, where we are going to do register renaming, allocating entries in the RS reservation station and ROB, and advancing from the dispatch buffer to reservation station. And in the instruction execution, we issue ready instructions to be executed, and executing the issued instructions and forward the result to all the places. And then the instruction completion will be done in the program order. So again, like instruction scheduling, there are again multiple designs out there, which is basically like all the in-flight instructions which are there in the reservation station, reorder buffer, and so on. And so it also consisting of the associated wake-up logic and the select logic, which instruction to be selected, and how do we schedule that onto the functional unit. When we are scheduling whether we are going to read the register file or whether the data is already available with the reservation station, depending on that, the designs are going to be varied. If you consider one model where we'll schedule the instruction with the data capture, where what we are going to do is basically, so whenever functional unit finishes execution, data will be forwarded to the reservation station, and the data also is going to be updated in the register file. And now what we are doing is, from the register file, we'll be reading the operands and put it into the reservation station. So now, when we say instruction scheduling happens from the reservation station. And here, when we are actually going to the reservation station to read the data is already available in the reservation station entry. And if we consider this type of design, we eliminate the register file access from the critical path. If the instruction is ready, we directly take that instruction and schedule onto a functional unit, rather than reading the data then from the register file and so on. Because if you are going to do that, register file access is going to take some time, and which degrades the performance. So that is what is considered in the other design. For example, if you see without data capture, here what we are going to do is, if you see, we just send a wake up signal to the reservation station, and from there we'll be taking the instruction. Now, before this instruction is going to be scheduled onto the function unit, we'll now go to the register file and read the operands from the register file, and the operands are now given to the function unit. So now here register file access is in the critical path, even though we know that the instruction is now ready, but we have to read the values from the register file. Whereas in the previous case, the values are already available in the reservation station, so I can directly issue that instruction onto the function unit. So the trade-offs will be with the data capture design. Each reservation station entry is a bulky entry, because each entry you have to actually store the operand, and operand may be a 64-bit value or whatever, for example. Then you need to have a wider entry in the data capture based reservation station. But without data capture based thing, you don't need this 64-bit field for each of the operands. Maybe you require only a 10-bit or 15-bit of tag, or some number of bits of tag, and that will be very less compared to your actual operand. So that means you can design a reservation station with the lesser number of bits, or the size of the reservation station will be very small in the case of without data capture model. But the penalty you pay is register file access is in the critical path. So now the design trade-offs are there. Either you want area efficient one at the cost of extra latency, then go for this without data capture. But so if you don't want the penalty in terms of performance, then you have to go for an increased area for reservation station, and so that your register file access is completely eliminated from the critical path. Again, these are like multiple the design points in your entire design space. As I mentioned in the last class, right, the entire architecture is basically design trade-offs. You will have multiple points, and you can select one point depending on your requirements. If area is the main constraint you have to solve, then you have to go for without data capture based design. But the performance is the major thing for you, then you have to go for with data capture type of design and so on. Right. So this is about the execution of instructions in out of order fashion. by using different components of the superscalar processor. But so far, we have not discussed anything about the memory operations. And there are two memory operations, which are load and store. And how do we process this load and store instructions? That is what we are going to see in the next few slides. By the way, load and store is also again one type of instruction, and again you need to have a reservation station associated with that, which stores this load and store instructions, and from there we'll be reading the instructions and give it to the functionality. Here the functionality is nothing but the memory or the cache, whatever. So if I just again consider our dynamic execution core, and now if you see the reservation station associated with the load store, the last one is the reservation station associated with the load store, and we have so a buffer, a 3-entry buffer. It consists load and store instructions are going to be there, because it's effectively it is taking processing of load and store happens in a pipeline fashion, and multiple stages will be there before actually we access the data memory. We'll see that in the next slide. And here, because we know that the store operations in the complete stage will be writing to the store buffer, and in the retire stage we'll be writing the store value into the data memory. That is what is shown here. The complete to a store buffer and a retire to the data memory. That is what we are to do for a store operation. But whereas for a load operation, when we say load is set to be completed, then automatically whatever the value we read from the memory, that will be sent to the destination register specified in the load instruction. So how do we order these memory operations? In my program, there may be load instructions, store instructions, and there will be load. After that, there is a store, and after that, there is another load, and so on. There may be some dependency among these instructions. So how do we do all these things? When do we say two memory operations are dependent? If both are referring to the same memory location, then we say these two instructions are said to be dependent. But how do we check that? How do we check two ALU instructions whether they are dependent or not? There is a true dependency between two ALU instructions. What is that we do? Or what is that we discussed in the last class?
So raw dependency, right? Read after write.
Right. So, but how do we check read after write dependency between two instructions? Let us say add and multiply. Add R1, R2, multiply R4, R1, R5.
You have to check for the operands of the let's say corresponding to two instructions, whether the output of one is not blank.
No, are we going to check the data inside the register, or are we going to check only the register tag? Because the data dependency here, for example, R1 is the destination operand in add instruction. R1 is the source, one of the source operands in the multiply operation, and multiply is coming after add. So because R1 is common there, so now we say multiply is data dependent on add instruction by just looking at the register address, right? This is the R1. We are not looking at what is there inside the register. We just look at only the register, the name of the register, identity of the register, which is like a register tag or whatever. So in the case of ALU operations, all we need is just compare the registers. Whether both are using the same register, then we'll easily identify whether they are dependent or not. But how do we do the same thing in the memory operations? What can be done in the case of memory operations? Are we going to specify the memory address directly in the instruction? Any idea? Let us say I want to read the data from an address location X. Am I going to give X directly in the instruction or not?
I think the address will be supplied if, let's say, if you want to access memory.
Right, but are we going to supply X directly? That's the question. Or something else we use?
It depends. I mean, let's say if addressing modes are used, then you have to specify the memory and there are some offset also.
Right. But let us say we consider, for example, RISC type of systems, and also assume that each instruction is 32-bit width, and my main memory is of 4 GB. Right? And if it is a 4 GB main memory, That means how many bits are there in the physical address space?
2 raised to 32, right?
Right, 32 bits are there for specifying the address itself. Now, if my whole instruction is 32 bits, how can I specify this 32-bit address in the instruction? And similarly, again, if you generally look at, because the load instructions, these are like generally generating they generate only if the system is supporting virtual memory and so on, it generates a virtual address. And in 64-bit architecture, if you see, the virtual address is typically 48 bits. And how do you specify this 48-bit address in a 32-bit instruction? That's not possible, right? So generally what we do is, for the memory operations, we are not going to directly specify the address in the instruction itself. We will be specifying the address in terms of two components. Basically, if you see the segmentation, right? How do we implement the segmentation? What addressing mode is used for segmentation? We use base and offset. Segment base is given and an offset is given. So we have to use that base and we have to add the offset to that. Then that will be your effective address. And you use that address and then go to the memory location and then read the operand from there. And how are we specifying this? Because when you have the base is stored in a separate register, base registers, right? So there are a set of segment registers are associated with the system. And by looking into those registers, we'll get the base address, and the offset is specified in the instruction, because offset is like a fewer number of bits and so on. And so as a result, your 32-bit instruction or whatever can easily accommodate this offset. So these memory operations address are not directly given in the instruction. It will be given as a two components, and you have to perform addition of these two, then you'll get the effective address. Unless until you perform this addition operation where base and offset added, you are not going to get the effective address. Unless until you get the effective address, you cannot identify whether two memory operations are dependent or not dependent. Unless until you perform all these things, that means you have to take this memory operation through the execute stage and compute the effective address. Then only you know what is the exact address this instruction is looking at, and then you can compare this address with the address computed for the previous memory operations, and then see whether these two are dependent or not. And also another thing is, for example, when we are specifying the effective address as two components, let us say address is 1000. 1000 can be specified as 900 plus 10, 100, or it can be specified as 400 plus 600. That means we cannot just look at the individual components and then say whether they are dependent or not. Unless until we perform the full addition, then only we know the actual dependency. So that's the reason why memory dependency identification is very tough compared to the ALU operations. Okay. So, but then if you want to enforce this ordering across memory operations, one simple option is just execute all these load and store operations in the program order. So if you are executing the instruction in the program order, then everything is taken care. Because whatever is given in my program, first load instruction, then store, then load, store, or whatever, I'll be just executing the same order one after another. That's a simple solution, but that is actually not a good idea, because we know that we have to give preference for loads over stores. There may be several dependent instructions waiting for the load value to be available, and there is not any instruction waiting on a store operation. Store is just right into the memory. In such cases, why can't we actually speeden up the processing of load operations by delaying the store operations? If we want to do that, then option one is not a good idea. But then what we are going to do is, and also another thing is like the stores. When we perform a store operation, we have to write the data to the memory. That means we are changing the state of the memory once we perform an operation. So in such cases, typically we should not alter the store operations. We execute the stores in the program order, right? But we try to see whether loads can be executed ahead of previous stores and so on in a speculative fashion and so on. So stores must be executed in the program order, mainly because if there is any exception or something happens, then you have to recover the state. And for that reason, we'll just use the stores in a program order execution. Or the option 2 is basically we execute these loads in an out of order execution. Out of order execution means even if the previous store is not yet done, we just go ahead and execute the store load operation, subsequent load operation. Because we know that if we service the loads as early as possible, the values will be available and the dependent instruction can start executing on the functional units, which can improve the overall performance. But in such cases, what we have to do with the previous stores is we just write the stores into a store buffer. But once we write the previous stores into a store buffer, not into the memory, and if there is a subsequent load comes up, then there may be a problem of read after write. Okay. So for that, what we have to do is whenever any load we want to execute ahead of stores, we have to just go through the store buffer and see if something is there in the store buffer. If it is so, we'll forward it. If not, then we just execute the load completely in a speculative fashion, and we'll put that speculative bit on in the reorder buffer. And later point of time, if you identify that, okay, this load actually depended on the previous store or whatever, then we have to just roll back all the load and the dependent instructions executed afterwards. Those things we are going to discuss in the next couple of slides, and the associated hardware components to implement these points, whatever I discussed. If you see an example here, there are two stores and there is a load. And now this load actually is not dependent on any of the previous stores. I can actually execute this load. Load can bypass the earlier stores. Of course, here for the simplicity's sake, I've given addresses X, Y, Z directly, but which is not the case. It will be given as a two components, and then you compute the effective address. After that, you'll know this is what is the effective address of each of these instructions. And in the second case, we have store X, store Y, and load X. So here the load is actually trying to read the data from the previous store. So now first store can actually forward the data to the load. So we may have this type of scenarios when we are dealing with the real applications. A previous store can forward the data to a load, or a load can bypass all the previous stores. And depending on this, we have to actually see these things at runtime, and based on the scenarios, we have to either bypass the load or take the data from the previous stores and so on. So when we are proposing the corresponding hardware components, then we need to take care of these things. So if we just closely look at this load store unit organization in the superscalar processor, it will be something like this. There is a reservation station associated with the load store unit. That means all the load and store instruction coming to that reservation station sitting there. And because the load and store two separate instructions, now we split that. Depending on whether it is a store or a load, we are going to send that to the corresponding things. If it is a load operation, we'll send it to the load pipeline, which consists of three-stage pipeline. In the first stage, we'll be generating the address. When I say address generation, which is nothing but adding these two components, X and Y, a base and the offset. And then that is going to give you an effective address. Then what is that we are doing? Address translation. Why we have to do address translation here? What is the need of going for address translation here? I think this is already discussed in the yesterday's lecture, one of the lectures.
I think the caches store only virtually indexed and physically tagged. So
right.
We need...
Yeah. So basically, if it is a virtually indexed and physically tagged caches, right? So there we are going to have, in that case, we can actually index it with the virtual address, but the tagging is happening with the physical. VIPT, right? Virtual index and physically tagged. But that is the cache designs and so on. But here we are just looking at only the load instructions. Let us say, or simply you can consider our caches are completely physically addressed and physically tagged, PIPT. But first of all, what is happening is like your underlying system is supporting virtual memory. Once the system is supporting virtual memory, whatever the addresses generated by your applications are actually the virtual addresses or logical addresses. That you need to convert into a physical address. That is where we have this address translation. And that is where we'll see to optimize this. Otherwise, like address translation, for that you have to go to a page table which is stored, which is there in the main memory and which takes a lot of cycles. So we'll go for a translation look aside buffer TLB. And from there, we'll get the translated address and so on, right? So it means once we generate the address here in the first stage, we take that and give it to the data TLB, and data TLB is going to give you the translated address, and that is the physical address. And using that address, we'll go to the data cache and read the data from that. And that data will be supplied to the processor which issued this load instruction. That is the reason why we have 3 stages here: address generation, address translation, and the actual memory access. In the case of store, what we are going to do is, the first stage of the store processing, we generate the address similar to the load, and the second stage similar to load, we are performing the address translation. And after that, we have the effective address. That means effective physical address, and where we have to actually store the data. And then, instead of directly accessing the data cache in the third stage, what we are going to do is we'll just write that to the store buffer. And once we write to the store buffer, according to the system, the store is said to be completed. But we'll be taking the store instructions from here, and then we'll be writing to the data cache the later, right? So basically what we are going to do is, first we will be finishing the store operation by writing into the store buffer, and then taking the values from the store buffer. When it comes to the head of the ROB, the store operation, then we'll be moving that from the finished store buffer to a completed store buffer. And at the time of retirement stage, we'll be taking the values from this completed store buffer and actually writing to the data cache. In other words, basically a store operation, the 2 critical operations are address generation and address translation. After that, we'll be just writing to the store buffer. That's it. If you have enough number of entries in the store buffer, you can keep on accumulating your subsequent store operations into this buffer. But if the buffer is full, you cannot store any more new store operations into it. So in that case, you have to stop servicing any load operations by the data cache and try to take the instructions or the data from the store buffer and put it into the data cache, so that you will make some free entries in the store buffer. So that is what we have to do. This is basically the organization of load store unit in superscalar processor. One for the loads and the other for the stores. Now, if you are going to issue this load and stores in the program order, no matter whether it is a store operation or load operation, then this is what is the design. But we want to implement, for example, the previous case, whatever I considered, right? So if you see here, there are 2 cases. One is a load bypassing, the other one is a load store forwarding. How do we implement these things? If you want to implement this, what changes we have to make to this particular design, right? So we'll see the first part. If you want to implement load bypassing, compared to the previous organization, when do we do the load bypassing? Our load, which is independent of the previous stores, then load can directly go to the cache and then read the data. That is what the basic idea of load bypassing. That means first I have to check this load with all the stores sitting in the store buffer. How do we check that? So we are going to have, in addition to this here, in addition to the store buffer entry, for each entry, we are going to have extra field that consists of the tag or the address. Now we take the tag of this load instruction and search in the tag field of the store buffer. If there is a match that indicates that this load is actually dependent on one of the stores, then I cannot bypass that load. I cannot go to the cache with that load address and then try to read, because this data is going to be updated by the entry in the store buffer. If there is no match indicating that this load is free to access the data cache, because none of the store instructions you are waiting in the store buffer are dependent on this particular load. There is no match with the address, so the load can be peacefully go ahead with accessing the data cache. That is what we are going to do. If there is no match, then we read the data from the data cache and will update in the destination register and then proceed further. But if there is a match, then we cannot proceed further. And again, when they are implementing the load bypassing, in order to reduce the overhead associated with this store buffer, they generally don't consider the full tag bits. Typically, you can consider like 19 to 20 bit of tag for the address, right? But you don't need that much tag. You can just actually consider fewer number of bits, because if you have a fewer number of bits, tag comparison takes less amount of time, and the total overhead storage requirement is also reduced. So typically, if you want to consider, because all we need is just whether it is matched or not. So for that, we can consider a partial tag here. But the penalty is the partial tag may match, but the full tag may not match. So there may be sometimes it may degrade the performance, but the storage point of view, it is better. So that's the reason why if someone is implementing load bypassing, they generally don't consider the full tag. But if you want to forward the data from a previous store to a later load, then we need to consider a full tag, because we cannot just match based on the partial tag and try to supply the data from a store to a later load, right? So in the forwarding case, we need to have a full tag here. And if there is a match in any of the entries of the store buffer, then the data in the data field is forwarded to the load instruction. So that means the load is now is not necessary to access the cache. It directly gets the data from the store buffer. So that way, like, because the store buffer access is taking less amount of time compared to the data cache access and so on, and that also is going to add benefit to the overall performance. But here it adds extra complexity, because you need to consider full length address bits, not the partial tag, and you have to consider priority encoding to be implemented, because there may be multiple stores to the same address, and then there is a load instruction. Now, which store has to supply the data to this load? The latest store has to supply. So that is where we have to implement a priority encoding and give the priority preference for the latest store. And also another thing is we need to have extra read port in the store buffer, because previously we have one read port through which we read the data and write it to the data cache, but now we need to have extra read port to supply the data to the destination register and so on. So slight extra complexity is there if you are going to implement the forwarding part. But here, if you see load forwarding or load bypassing, we simply assume that the load and store instructions are issued in the program order. But we already discussed for the ALU operations, the instructions can be issued in an out of order fashion. Why can't we do that here? Yes, we can do, but for that we need to have some more extra components. You can clearly see here. So, the reservation station consists of loads and stores. I can pick some load instruction in an out of order fashion, and I can just start generating the address, translating the address, and trying to access the cache. Okay. Once the address is translated, then we'll be comparing with the tags of the previous stores that are there in the store buffer. And if there is a tag match at the store completion, then so that is what we are going to do. If there is a match, right? Basically, like what we are going to do is like we'll be supplying the data directly from the store buffer. But if it is not matched there, and then we go ahead with the data cache access. But because we issued the load in an out of order fashion, what we are going to do is we treat this load instruction execution in a speculative mode. And when we are executing the load in a speculative mode, we'll come to this finished load buffer where we place the address and we place the data, whatever we access from the data cache, and supply this data to the destination register, so that dependent instructions also going to execute in the speculative mode. That is indicated with the bit, speculative bit in the reorder buffer. Now, at the time of the store completing, store is coming from a finished store buffer to a complete store buffer, we take the tag of that, and now we search in the finished load buffer. If there is a match that indicates our earlier load wrongly executed, and we have to fetch that load, and all the subsequent operations which consume this load operation needs to be flushed or replayed, and that is what is given here. So if you see here, if there is a match with the tag address with one of the addresses of this load in the finished load buffer, now we need to flush this particular load. Also, all the trailing instructions consume this load. But if there is no match, then you are fine, because if there is no match with this load instruction to the all whatever the stores which are there in the store buffer, I'm fine. And at the completion time, we'll just simply write this data and update the architectural register and so on. So the advantage what we are going to get with this out-of-order execution of loads is you need not wait for executing the previous stores. I can just go ahead in the program and look ahead and advance my pointer and then read some load instruction and then start executing. But of course, I'll be coming in the program order for the remaining operations and so on. But rather than just in the normal case, what we are going to do is we first execute the first instruction, first memory instruction, next memory instruction, and so on. But now here, because loads are given priority, we just try to read the loads as much as possible and then try to process them quickly. And slowly we'll bring the stores and so on. But only thing is, whatever the loads you brought and execute in a speculative fashion, you need to have a space in the finished load buffer. As long as there is an entry in the finished load buffer, you can keep on taking the load instruction and process, because all these are going to be sitting in this finished load buffer. And when the load comes to the head of the ROB, by the time already, if any of the previous stores are there in the program order, they might have already completed and so on. And if they have not created any issue, then I can just go ahead with this load and then execute or writing into the architectural register. So that way, like, I'm going to get the benefit if you use this out-of-order execution. And typically, the current processors are implementing this loads in fully in out-of-order fashion by adding these extra buffers. For loads, anyway, we have, for stores, we have finished store buffer and completed store buffer, which is the same buffer, but the pointers changing and so on. But in the case of loads, we need to have extra buffer, which is a finished load buffer, which is nothing but we access the data from the data cache, but we have not written to the architectural register. And all those such load instructions are going to sit in this buffer. And every time when there is a new store comes up into the buffer and so on, we will be checking the address of that store at the completion time with the addresses that are there in the finished load buffer. And also there are techniques proposed to check whether the loads are dependent on the previous stores and so on without actually computing the effective address. There are some prediction methods. And using that, if the predictor says, okay, this load is not going to be dependent on the previous stores and so on, then just go ahead and then execute the loads in a speculative fashion. Otherwise, you have to just wait for the actual address computation and then compare with the stores and so on. And to further improve the processing time of loads and store operations, what we can do is we can actually consider these dual ported and non-blocking data caches. The caches are two types. One is a blocking data cache and the other one is a non-blocking. Blocking data cache means if you are servicing a request, when we send a load or a store to the cache cannot accommodate any further request unless until the previous operation is done. That is what is called as a blocking cache. But typically, if you consider Core i7 latest processors and so on, right, the L1 cache itself is a 4-stage pipeline. That means, because typically when you have an address given to the data cache, what are the steps we do? We send the address, the set bits to the set decoder, which is going to activate a particular set. And then we'll be reading the data from the data side and the tag from the tag array. And then we'll compare the tags. And if there is a match, then we'll read the appropriate data from the corresponding data side and then supply the data to the destination register. So this consisting of set decoding, reading the data from the arrays, comparing the tags and supplying the data, 4 stages. So you can actually divide the cache into 4 different stages. And now if you want to pipeline the caches and so on, so typically what we can do is like we can also consider this non-blocking. So where once if some request is there, so we'll be processing the request in a pipeline fashion. And also in addition to that, we'll be having a miss status handling registers associated with the caches. That means if the previous operation, memory operation is a miss in the cache, in a blocking cache, until unless the data available from the next level cache and so on, this cache is not servicing any subsequent request from the processor. That degrades overall performance. In the non-blocking, if there is a previous request miss, it sends to the next level, but now cache is free, it can take the next request from the processor and so on. But the previous request, it is storing in the miss status handling MSHR, and the request will be sent to the next level cache or memory or whatever. And this particular cache is now keep servicing the subsequent requests and so on. So you can reduce the overall memory access latency if you can send non-blocking caches, and that is what typically the current processors are using. This non-blocking caches, pipelining caches, all these are used mainly to improve the overall performance, because even if your processor is efficient in terms of processing the requests and so on, and unless until the processor gets the data which is there in the caches and memory, the overall performance is not going to be improved. And that is where we need to consider optimization techniques for the caches, the memory, and so on. Of course, in the afternoon session, I'm going to talk about how the DRAM based memory is organized and so on. You'll see there some more optimizations at the memory level and so on. If we consider this dual ported non-blocking data caches, so it will be something like this, because if you want to process multiple loads simultaneously, I can consider multiple pipelines for the loads itself. Of course, stores are not that critical, so we'll be using one pipeline stage for that, one pipeline unit, but the other ones are like typically 2 units for the loads. Basically here, I'm going to process 2 load requests simultaneously in each cycle. And to support these 2 requests, then the data cache is also now non-blocking, so it can keep reading the data and so on. And if there is a miss, then I'll be sending that to the MSHR, and then the request will be sent to the next level and so on. So this way, like overall performance of processing load store operations can be improved in the processors. Okay, so the major objective of any of these memory operations is like basically you have to improve the memory bandwidth and reduce the average memory access time, so that the performance of the whole system is going to be improved. Right? So with that, I completed the superscalar part. Now I'll be maybe another 10-15 minutes. I'll talk about this Nehalem processor core, how the pipelining is considered, and whatever we discussed, rename registers, reorder buffers, load store queues, all those things, we'll see how that is implemented in the real processes. Of course, this is like Nehalem is not a new one, because now the Intel new architecture, Skylake, and many other things, Ice Lake and so on are there. But this is, I think, this consisting of several innovative components and so on, and the later designs also adopted almost the same things. So that's the reason why I just consider this. And you can find this paper on Google, and I think it's a 30 or 35 page report explaining the entire Nehalem architecture in detail. So those who are interested can look into this paper. And I'm taking the material from that paper. So
I have
yeah.
a question about the previous method that we discussed.
Right.
Yeah. So here, I mean, there is this finished load buffer, and you did mention about the reorder buffer, right? So how exactly, when exactly does the data go from finished load buffer to reorder buffer?
No. Here, this is like a finished store buffer and completed store buffer.
Yeah. So I mean, any other instruction that comes, I mean, that depends on this load, must be looking at the reorder buffer, right? To, I mean,
reorder buffer, we are making an entry into reorder buffer whenever we are dispatching the instruction to reservation station. That's it.
Yeah.
And
so
the operand for that is actually available if it is a captured based scheduling, whatever we discussed in the previous slides. So then in the reservation station itself, the operand is going to be available. If not, then the tag is going to be available.
Right. So, but you also mentioned in passing that the speculative bit will be set, and when you find that,
right.
So in that case, how is a distinction made between different speculations that were made? Like, say, there was also a simultaneous control speculation that was happening, and this is also happening at the same time. So how is this?
But doesn't matter, right? I don't care about, as long as if I'm executing not in the correct way, I'll just set the bit. And when the instruction comes to the head of the ROB, if the bit is still set, I'm not going to commit. That's it. Whether this is coming from a misspeculation or coming from an out of order execution or whatever, right?
Right.
So then it doesn't matter.
Right. So I think the question I'm trying to ask here is how is when is the speculative bit considered even? No, I mean not just in this case, but in general, When is the speculative bit looked at? Only when when the entry is at the top of the buffer, or do you flush it?
Right. No, right. So what I'll do is, like, for example, let us say there is an control instruction, a branch instruction.
Yeah.
And we speculated that the branch is going to take place. And then we start executing the instructions in the predicted path. Now, when we are going to start fetching the instruction from the predicted path and decode the instruction, and then when we are dispatching to the reservation station, because we know that we are in the speculated path, and because when we are dispatching an instruction to the reservation station, we are making an entry into the ROB also, right? At that time, we are going to set the speculative bit for that particular instruction. And that will be there. And it will just keep on processing, committing the instruction at the head of the ROB and so on. And once, let us say, we issued this instruction at time 10 and at time 20, this becomes the head of the ROB in the entire ROB, and you have to commit. But at that time, for example, if already the speculation is resolved and so on, the branch outcome is resolved and the speculation is not there, it's actually the correct execution, then we can just reset that bit anytime, and then we'll just commit this particular instruction. But when it comes to the head of the ROB, but still the speculation is not resolved, let us say. So you either have to stop that until unless the branch is going to be resolved, right? Basically, what we are going to do is at the time of commit, we will be checking that bit, and depending on that, we are going to take a decision whether we have to roll back this or not. And in the case of even the loads also, there may be a load speculatively issued, and then the dependent instructions are actually consuming from a speculated instruction. If any instruction consuming data from a speculatively produced instruction, then automatically that dependent instruction is also going to be executed in the speculative path. So you keep on adding that bit to all the dependent instructions. And at any point of time, if I want to roll back, then I'll just come to the ROB and then flush all the instructions with this speculative bit set to 1.
Right, yeah, that's where I have the question. So when you're flushing all the instructions with speculative bit set to 1, you're not just flushing the instructions related to this instruction. It's doing everything. Right?
Instruction execute.
No, see, like in this context, we're talking about this one particular load, which might have been a dependency for subsequent instructions. So, and once you find that this load speculation has not been resolved yet, you go back to the buffer and flush everything that is set to 1, right? Like the speculative bit is set to 1.
Right. So I'll just give you a scenario. Let us say we just consider this load, and there are 2 instructions which are trying to consume the value produced by this load instruction. There's a load, add and multiply. These 2 are actually consuming the data from the load. Okay. So now we executed the load in a speculative fashion. So now we set for the load also, we set the speculative bit, and add consume the value from this load. So add is also going to have the speculative bit set, and multiply also the speculative bit is set to 1. Now they are executing normally, right? And after some time, let us say the load, it compared with the tags of the stores and so on, and none of these matched. So that indicates this load is perfect. Now we can just reset the load bit, and also we reset the add and the multiply part. But if that is not the case, for example, there is a store which matched with the load address, then I'm going to reset, I'm going to invalidate the load, and also I'm going to invalidate the add and the subtract. That is what is going to be done. And not only this, but actually in the superscalar process, they also consider dependency tree is constructed. That means every instruction, whichever is taking the values, it is going to construct a dependency tree which produce the value for this particular instruction and so on. So, for example, if there is a load instruction, this says, okay, load is produced by, produce a value which is consumed by these instructions. When I flash the load, the entire nodes in the dependency tree are going to be flashed. That is also going to be there. Of course, it's not discussed here, but the dependency part is also going to be constructed.
Right. I think that is what I was looking for. Like that, there's some mechanism like that is what I was.
It is going to be there.
Okay. So
that takes care of. Yeah.
So would that be part of the hardware again, or?
Yes. Yeah. That will be implemented. But also another thing is actually, so when we, for example, a simple case, right? So if we consider, again, we come back to the control instructions. When there is we predict something and then we execute the instruction in a speculative path and so on. Now, what we typically do is if the speculation is wrong, then simple cases we come to the pipeline and then flush all the instructions. But sometimes what happens is it's not necessary to flush all the instructions after this particular thing, even the load case also. There may be, after load, there may be 2 add and multiply instructions. After that, something else also there. But these remaining instructions are not consuming any value from the loads. In such cases, actually, we don't have to flush those things. So when we say pipeline flush, you are flushing the entire pipeline. That is actually sometimes degrade the performance. And some other cases, what they do is a selective replay they consider. In the pipelining, when you are flushing, you just flush only those instructions which are consuming the value from this specific one. That is where this dependency tree also comes into picture. So the selective replay, which is like replaying only the selected instructions, is generally going to give you a better performance compared to flushing the entire pipeline and so on. These are the optimizations that are proposed in the architectural research and so on. But generally, we are not going to discuss those things as the basic material and so on. But yeah, you can find plenty of material related to these things. Okay.
Yeah, thank you.
Right. Yeah. Right. So if we consider the Nehalem core, there is like a multi-core system, but we are just looking at only single core. Within the single core, if you just see the pipelining, you can see there's an instruction fetch and pre-decode. Then there's an instruction queue. That means a pre-decoded instruction is going to be placed in the instruction queue. From there, we'll be taking one instruction at a time and we'll decode that. And then we'll have a rename logic, whatever we consider register renaming. Then we have a reorder buffer that they call it as a retirement unit. And then there's a scheduler which is going to take the instructions and schedule onto these reservation stations. Then we have the execution units. Now, if we just look at this entire pipelining, so there are like 16 cycles, 16 stage pipeline you can consider, and the front end consisting of instruction fetch, pre-decode, instruction queue, writing to the instruction queue, and the actual decode. And the execution engine out of order part consisting of this rename logic, retirement, or reorder buffer, and making an entry into reorder buffer, writing into reservation station and taking the instruction from the reservation station and scheduling that onto the functional units. And now from the memory side, we have, because systems are supporting virtual memory, so we need to translate the address. That is where this instruction TLB and the data TLB, that is like a split TLBs at the level 1, and you have a unified TLB at the level 2. Similar to the caches, TLBs also have multi-level TLBs, L1 and L2. L2 is unified, L1 is split. In the case of caches also, you have a split caches at the L1, level 1 instruction cache, level 1 data cache, and level 2 unified cache consisting of both the data and the instructions. And then after that, there is a L3 and main memory and so on. This is the memory part of this thing. Now, if you see this front end in order part and the execution is out of order, we'll just focus on the front end part. Can anyone tell me why we require a pre-decoding and then the decoding? What do we do in the pre-decoding part? Any idea?
In pre-decoding, we might be just trying to decode what type of instruction it is, like whether it is control flow or.
But then what do we do in the decode?
We take out the like separate register operands and like all that.
But actually, I'll give you a hint. This is for an Intel processor. And Intel follows the CISC philosophy. Now, can someone tell me the logic?
It could be due to variable length instructions, so we might have to do some additional business.
Typically, your CISC instructions are complex in nature. Multiple things are packed together into a single instruction. And CISC philosophy is the old philosophy, right? When Intel came up with this CISC ISA, at that time, memory was very costly. And because your memory is costly, you have to use the memory, limited amount of memory efficiently. What they have done is like they pack multiple things into the memory And when they go to memory, just bring a large chunk of data, and then in the processor, they are going to just do all this pre-processing and so on. Multiple instructions can be mapped, packed into a single thing, and also they supported like addressing modes where an instruction consisting of one operand maybe from register, one operand maybe from the memory, and so on. All type of things are there in the CISC. And to do that, because variable, the length of the instruction is also not fixed. But later, RISC came into picture, and they looked at the disadvantage of all this, the CISC type of philosophy. And also by the time RISC came up, the memory became cheaper, and also they implemented this pipelining and so on. And to implement the pipelining efficiently, you need to have a simpler instructions, a fixed length instruction, 32-bit instruction. And also they consider load store architecture RISC, saying that all the ALU operations should get the values from the registers only. No memory operand should be there. If you want to access the memory, you just use a load and store separate instructions and so on. So they came up with this RISC philosophy, and which actually process the instruction in a pipeline fashion efficiently. But now for the backward compatibility, Intel has to still stuck with the CISC. But if you want to implement at the hardware level, efficient mechanisms are there for the RISC. So that is where what they have done is, for the backward compatible, they still use CISC instructions, but they take the CISC instruction and convert that into a set of micro instructions. And then they operate on the micro instructions. So that means outside loop, they still follow the CISC philosophy, but inside they actually do this RISC processing. That is what is done. And for that reason, we have this pre-decoding and decoding part. And if you see here in the front end, so we will be reading instruction from the instruction cache, and who is going to specify where the instruction is there? PC is going to specify. But for that, actually, because there can be a branch instructions and so on. So if there is a branch instruction, so we need to take the help of branch predictor. That is what is given, BPU, branch prediction unit, and which tells whether the branch is going to take place or not. If it says branch is going to take place, then we have to consult the branch target buffer and get the target address, and we consider that as the next address, and we go to the instruction memory and read that particular data from the instruction memory, right? And that is what we have done. And because it's a logical address is generated, and then we have to convert that into a physical address. For that, we are going to access the level 1 TLB, ITLB, or the level 2 TLB. And finally, we will be getting the address, and then we'll go to the cache memory and get the actual instruction. And we'll be supplying 128 bits per cycle from that instruction cache and put it into this ILD, instruction length decoder, which is going to decode the total length of this instruction. And then what we are going to do is, you can see here 6 macro instructions per cycle can be taken and then be pushed onto the instruction queue. And from this instruction queue, which consisting of which can hold 18 entries, and 4 macro instructions can be considered every cycle, and they can be given to the decoders. There are 3 simple decoders and 1 complex decoder. And this MS ROM is effectively micro sequencing ROM, which actually consists of, for a complex instruction, that is a square root function and so on. So you don't have to do the decoding every time. So you can just have a sequence of operations that is loaded into this read-only memory. If such instruction comes up, we just index into this ROM, and then we read the sequence of micro instructions for that macro instruction. And we'll be taking this and then sending up to 4 micro instructions to this instruction decoder queue, IDQ. And here this also has a loop stream detector. That means, for example, and this IDQ has 28 entries. A simple case is, let us say I have a loop in my program, and all the instructions of that loop, if you put together, is less than or equal to 28 micro operations. Then once I detect that actually the program is in the loop and executing the loop multiple times and so on, then I don't have to perform this fetch, decode, pre-decode, decode, and so on, because everything decoded instructions are already there in this IDQ. That is the advantage of loop stream detector. This is going to detect whether we are running a loop or not. If it is running a loop, then already decoded instructions are there, and then it can just sequence through the micro operations and so on. And every cycle will be taking 4 micro operations, and they will be issued to the next level. And it consisting of this out of order execution engine. From the IDQ, we'll be taking 4 micro operations and we'll be running through this register alias and allocator, which is basically register renaming will be done. And then we'll make an entry into the reorder buffer. And you can see to accommodate up to a maximum of 128 in-flight instructions, reorder buffer consists of 128 entries. Huge reorder buffer. And we'll make an entry into the reorder buffer. And when the instruction comes to the head of the ROB, then we'll be writing into the architectural register. That is what retirement register file, where we actually consider AR of architectural register file, but this is here we are considering retirement register file, some naming convention, but both are same. And Intel uses a unified reservation station. So every cycle we are going to take 4 micro operations that will be issued into this unified reservation station, which can accommodate 36 entries in it. And as I said previously, unified reservation station has a drawback of multiple ports, and that is what they consider. But they want to make use of 36 entries efficiently, and that's the reason why, even though there is a complexity of extra ports, here you can see 6 ports are there. Every cycle, 6 different instructions can be read from this 36 entry unified reservation station, and the values will be given to the appropriate functional units, integer units, floating point units, load unit, store unit, and different things and so on. And a store operation, you have an address and the data. Data will be stored in the store data buffer, and the address will be sent to the store address pipelining part. And here the execution part is going to be done in an out of order fashion. And if it is a memory operation, that means anything which is there in the load or a store, and it will be going through this memory order buffer, MOB, which consists of load queues, store queues, load fill, different things are there, and through which actual communication happens to the data cache, either writing the data to the data cache or reading the data from the data cache and so on. This is what is going to happen inside a superscalar processor, the real superscalar processors and so on. We already discussed all these architectural register, rename registers, reorder buffer, reservation stations, and the same thing is there in this. Okay. And of course, the memory order buffer I have not discussed, because typically when we consider the memory component, then we can look at what is there inside this memory order buffer and how this data caches, TLBs are accessed when the requests are going through that and so on. But yeah, if you look at this paper, you will find the information about the full details about this Nehalem architecture. Okay. And yeah, with that, I'm done. And we have another 5 minutes. If you have any questions, you can ask me. In the afternoon, what I'm going to do is like at 2 o'clock, I'll be taking the next class where I'll be focusing on the DRAM memory organization, and also I'll briefly touch upon memory consistency. I think in the previous lecture, you might have already learned the shared memory, multi-core or multi-process systems and the cache coherency. And I'll briefly touch upon the memory consistency part. Those 2 things I'm going to discuss in afternoon's class, 2 to 3:30. Right? If you have any questions. But I strongly suggest you to go through this paper. Full details. Even the Skylake architecture is also there. Skylake microarchitecture. You can actually look into that and see what is really implemented in the process, rather than just looking at only from the textbook side of the information.
Thanks, Madhu. So
yeah, thanks.